Welcome to Week 7 Advanced Machine Learning Algorithms. This week, first we'll start with Introduction to Ensemble Learning. Day 2, we'll be looking at bagging and random forests. Day 3, we'll be looking at boosting and gradient boosting. Day 4 will be Introduction to XGBoost. Day 5, we will cover Light GBM and CAD Boost. Day 6, we'll be handling imbalanced data. And for day 7, we'll do our ensemble learning project where we will be comparing models on a real data set. So let's get started with our week 7. Welcome to week 7, our day 1, Introduction to Ensemble Learning. Today, let's dive into first the concept of ensemble learning. Now, what is ensemble learning? Ensemble learning is a machine learning technique that combines the predictions of multiple models to produce a final output. The idea is that by aggregating the strengths of several models, the ensemble can achieve better performance than any individual model. Now, why does ensemble learning improve performance? First, it reduces variance. By averaging predictions, ensemble methods smooth out fluctuations caused by overfitting in individual models. It reduces the bias. Combining weak learners can lead to a more accurate prediction, compensating for individual model weaknesses. And then it improves robustness. Ensemble models are more resilient to noise in data compared to single models. Some of the applications include fraud detection, medical diagnosis, recommendation systems, and predictive analysis, as you probably already have guessed. Now, what are the different types of ensemble methods? First one is called as bagging or bootstrap aggregating. The concept here is you train multiple models independently on different subsets of data created through bootstrapping. It's random sampling with replacement. Now, this combines predictions by averaging, which is regression, or majority voting, which is classification. Now, example is random forest in this case. Next, the strengths of this is it reduces variance without increasing bias. Next is boosting. The concept here is it trains models sequentially where each model focuses on correcting the errors made by the previous ones. It combines predictions through weighted averaging or voting. Example here can be ADA boost, gradient boosting, XGBoost, and light GBM, which we'll probably be looking at it in future. Next, we have the strength is reduces both bias and variance by focusing on hard to predict instances. Next one is stacking. The concept here it combines predictions from multiple base models or different types using a meta model to learn how to best combine their outputs. The strengths here it can utilize diverse model types to maximize performance. So these are the different types of ensemble methods that I'm going to talk about. But now, next, let's get into overview of commonly used ensemble methods. We have random forest, which we did last week, if you remember. It combines multiple decision trees using bagging. It reduces overfitting, common in individual decision trees. Gradient boosting sequentially builds models that minimize errors in the previous ones, suitable for both regression and classification tasks. We have ADA boost, which adjusts model weights based on performance and it focuses on misclassified instances. We have XGBoost, it's optimized version of gradient boosting known for speed and accuracy. And we have voting classifier, which combines predictions of multiple models using majority voting or averaging. Now, based on this, let's jump into a hands-on exercise where the objective is to build a basic ensemble model combining predictions from linear regression, decision tree, and KNN to observe the impact on accuracy. The dataset we'll be using here is the same iris dataset to classify flowers into different species. So we'll follow a bunch of steps. I think we're going to go follow 4 different steps. Our step 1 will be first to load and pre-process the dataset. So let's get started. It's a new file. Save as day 7 underscore exercise. And here first, let's go ahead and get the libraries. We need data sets from sklearn dot dataset, and I am going to import the load iris. Next, from sklearn dot model selection, I am going to import train, test, and split. Next, from sklearn dot preprocessing, I am going to import standard scalar. Now let's go ahead and load the data set. For that, I'm going to say data equal to load iris. Next, we need the features and the target. So for that, it's straightforward, data dot target. The data sets makes it easier for us to load the data. Next, let's go ahead and split the data set using the train test split, where we get x train, x test, y train, and y test. Again, this comes from train test split, and we'll pass x, the features, the target, test size equal to 0.2, and random state, my favorite number, 42. So I have that. Next, go ahead and scale. Some people ask me, why is 42 my favorite number? Is it my age or is it meaning of life? Now I let you decide that. Standard scalar, so scale features, standard feature, we're going to do that for train. We can say scalar dot fit underscore transform and pass it x underscore train. Next, for test, I'm going to do the same thing, scalar dot transform and pass x underscore test. So my features have been scaled. Our next step, step 2, is to train individual models. So we'll train the linear regression, decision tree, and KNN models separately. So for that, first I need them. So I'm going to say sklearn. Where is the logistic regression? That is available from linear model, and I am going to say import logistic regression. So I have my linear regression here. Next, from sklearn dot tree, I will import, got it right, decision tree classifier. And next I need KNN, which is coming from sklearn dot neighbors, which also again something that we have used before in one of the previous videos, neighbors classifier. So perfect. So I have all my three different. Now let's train individual models. For that, I am going to say train individual models. My log model, give a underscore, looks better, equal to logistic regression. For my DT or a decision tree model, I'm going to say decision tree classifier. For my KNN model, I think I missed a L over there, equal to K neighbors classifier. Perfect. Now let's fit them with the data that we have. Log model dot fit, and I'm going to pass x underscore train, y underscore train. So this is pretty much common for all of them. So next I want DT model. Next, KNN model. Okay, so that's perfect. So we trained individual models. Step 3 would be combine model into an ensemble. What we're going to do here is we're going to combine the predictions from the individual models using the majority voting for classification. So for that, I need some more libraries. Import numpy as np. We need from sklearn dot ensemble. I need something called as the voting classifier, and from sklearn dot metrics, I need accuracy score. Perfect. So I have all of them available. So first thing is creating our voting classifier. So I'm going to say ensemble model. I'm going to say voting classifier, and the estimators that I'm going to use here include You probably got it right. Log underscore logistic regression is log model. For my decision underscore tree, I have dt underscore model. Perfect. And for my KNN, I have KNN model. Perfect. So all of them look good. Next, another thing that I want to do here is voting equal to hard voting, which means the majority voting is the one that wins. So keep it this way. Perfect. Next, let's go ahead and train the ensemble model. So I'm going to say train the ensemble model. To do that, I'm going to say ensemble model dot fit x train y train. So copies from the previous one, so that's good. But next is predict with ensemble. To do that, I'll say y underscore pred underscore ensemble. I need ensemble model dot predict and pass it x underscore test values. So this will do my prediction. And now let's go ahead and evaluate the accuracy. I'll say accuracy score or accuracy equal to accuracy score now, and pass it y underscore test and my predicted, which is y underscore pred ensemble. Next, let's print this out. I'm going to say f ensemble model accuracy is accuracy colon 0.2 f. Perfect. So this will print my accuracy of the ensemble model. Now if you want to compare, the final step is to compare the model performance. I can do that by adding the comparison for all of them. So I can say let's start with saying evaluate individual models. I'm going to say y underscore pred underscore log equal to logistic model dot predict, and this one is x underscore test. I think this will stay the same for all of them. I'm going to say y underscore pred for decision trees is dt underscore model dot predict with this, and y underscore pred for knn equal to knn model dot predict. Perfect. Now let's go ahead and print all of them. So I'm going to move this below here, and I'm going to do 3 more for my others. Say logistic regression accuracy, which will be, I have not calculated that, so I'm going to say accuracy score y underscore test y underscore pred log. Right, so that's good. I'm going to take this and paste it for this and this. This one is decision tree accuracy. For this, we'll pass dt. Accuracy score is y test and y pred dt. Next one is my knn accuracy. Let's put it properly. K dash nn accuracy. Accuracy score is knn. Perfect. Y pred knn. And this one we already calculated, so we don't have to change anything for this. So let's go ahead and compare and run this. I'm a little excited for it. So let's go ahead and say Python day7 dot. So it looks like there's an error where it says missing one required positional argument x in this particular case. So let's go ahead and check it out. Right here we have scalar equal to scalar transform, and I see that I have not created this. So let's go back again, clear it out, run it. And there you go. We have the logistic regression accuracy is 1, this is 1, this is 1. Ensemble model is also 1. The reason is we are using a pretty solid data set of load iris. So that's why it is giving me perfect accuracy for all of them. But if you use a real life data set, you probably might see something different. But again, this is the way to kind of compare different models and see their accuracies, and also create an ensemble based on different models that you want and building into one single model from them. So I hope you are able to follow along and get this through. If you have any questions or had any issues with this, let me know and I'll get back to you. So, just to recap, today we got into learning and understanding the concept and importance of ensemble learning. We differentiated between bagging and boosting methods. We went and gained some hands on experience creating a basic ensemble using diverse models. And then we observed how ensemble learning improves model performance through aggregation. So, I hope this helps. And if you have any questions or have any follow up, let me know and I'll get back to you. Day 2, bagging and random forest. So, first, let's try to understand bagging, which is also called as bootstrap aggregating. Now, what is bagging? Bagging or bootstrap aggregating is an ensemble learning technique that trains multiple models on different subsets of the data created by random sampling with replacement, or also called as bootstrapping. The predictions of these models are then aggregated to make a final prediction using either regression, which is the average the predictions of individual models, or classification, where we use majority voting to determine the final class, which we have done earlier this week. Now, why use bagging? First, it reduces variance. Bagging smooths predictions by averaging them, reducing the effect of overfitting. It improves the robustness. By combining the predictions of multiple models, bagging creates a more stable and reliable ensemble. Now, applications is bagging is commonly used with decision trees which are prone to high variance. Now, let's talk about random forest. Now, what is random forest? Random forest is an ensemble learning method that builds multiple decision trees using bagging. It introduces an additional layer of randomness by selecting a random subset of features for each tree split. This makes random forest robust and reduces overfitting. Some of the key features of random forest include its bootstrap sampling. Each tree is trained on a randomly sampled subset of the data. Feature randomness: at each split, a random subset of features is considered, ensuring diversity among the trees. And prediction aggregation. In this method, we use regression for averaging the predictions of all trees, and classification to use the majority voting. Advantages of random forest include it handles both regression and classification tasks effectively. It also works well with high dimensional data, and it reduces overfitting compared to single decision trees. Now let's talk about the key parameters in random forest, which we used in the last, I think last week we used one of the project, where which has number of trees, which are also called as n estimators, which is the number of decision trees in that particular forest. And large values reduce variance but increase the computational cost in this particular case. We also use the maximum depth, which is max underscore depth, which limits the depth of each tree to prevent overfitting. Its shallower trees generalize better but may underfit. Then we use the feature selection, which is max underscore feature, a number of features to consider when looking for the best split. Options include the square root, which is square root of total features, default for classification this is, and we use log 2, which is logarithmic of total features, and none is use all the features. That these are the parameters. We did one with none in the last week. Next, we have the minimum samples per leaf, which is min underscore samples underscore leaf, which kind of talks about minimum number of samples required in a leaf node. Next, it prevents overly complex trees by ensuring each leaf contains enough samples. Now, based on this, let's jump into an hands-on exercise where the objective is to train a random forest classifier on a data set, tune its parameters, and evaluate its performance. The dataset we'll be using here is we'll use the breast cancer dataset, which is a binary classification dataset to predict whether a tumor is malignant or benign. So we will follow a bunch of different steps. To start with, let's start with a new file. Call it a Python file. Save it in my day2 underscore ex.py. Let's start with loading and pre-processing the data. Now, where does the data come from? It will come from sklearn dot datasets, and I am going to import from there load under. If I don't type properly, it will not help me. Load breast cancer. Next, I'll say from sklearn dot model selection, I will be importing train underscore test underscore split. Next, let's go ahead and load the data set. To do that, I'm going to say data equal to load breast cancer. Next, I'm going to use my features and target by using the shortcut data.data, and for targets, I'll say data.target. So I have those available. Next, I am going to split the data set with split the data set where we will get x train, x test, y train, and y test from train test split, and we can pass x, y test size equal to 0.2 and random state equal to 42. Now, next thing is we display the data set information. Now here I am going to say print. First, let's say features that it has is comma data dot feature underscore names. Next, I will do print the classes that it has, which is data dot target underscore names. So let's go ahead and print these and check how they look like. I'm going to say Python day 2, and there you go. These are the features that it has, and for like mean radius for the tumor, mean texture, mean perimeter, mean area, a bunch of different features and classes. We have malignant or benign. Our step 2 is to train a random forest classifier with the data that we have. So to do that, first I need the random forest classifier. Now that I can get from sklearn dot ensemble and import random forest classifier. Next, for metrics, I'm gonna get from sklearn dot metrics. I will import accuracy score and classification report. Now, next step is to train the random forest classifier. So I'm going to go here and say train random forest. For that, I'll say rf underscore model equal to random forest classifier, and I'll give a random state of 42. Next, I'm going to say rf underscore model dot fit the data, which we have x underscore train and y underscore train. So once I fit the data, next thing is all about prediction. So let's go ahead and predict y underscore pred equal to rf underscore model dot predict function and pass it x underscore our test data to predict the fields. So once that is done, let's go ahead and finally evaluate the performance of this model. To do that, first I will get the accuracy is coming from accuracy score, pass it y underscore test and y underscore pred. Next I'll say print. This particular case, first is random forest accuracy is accuracy. Perfect. Next I want to say classification report. Now that will be multiple lines, so I am going to say slash n classification report slash n, and to get the classification report I'll use the classification report function, and to that I'll pass the parameters y test and y pred. There you go. Perfect. So let's go ahead and run this and check it out. And to clear this out, I'm gonna not display them anymore and run it. So there you go. We have a random forest accuracy very close to 1, and our classification report, which shows bunch of different data. For a change, I think this model has better data as compared to others, and it gave us 0.98 instead of 1.0. But it tells us how well the model can predict based on the data that we have trained it with. Next, let's go ahead and tune some parameters and see if we can make it better. So we will go ahead and from sklearn dot model selection, I will import the grid search as CV, which where we can give some hyperparameters. Now here we will define the hyperparameter grid. This also we did in the last day 7 of last week, where we are going to give a parameter grid equal to, inside this, the ones that I'm interested in is n estimators, and we'll give different values and see which one it picks up best. 50, 100 and 200 I will use for my max depth, max underscore depth. I will use either uh, none, 10 or 20. And then we said features, so max features, as we mentioned, there's square root, there is what are those, we have square root, we have log 2, and we have none, which is all of them. So there you go. So these are our parameters grid. Now let's try to do a grid search and see which one is the best one. Grid search equal to grid CV, and inside this we'll have to give all the different functions or parameters, which is first is estimator. That is our random forest classifier with random state equal to 42. Next, I want to give the parameter grid, which is the parameter grid that I created. Next, it needs CV cross validation equal to 5, and I'll say scoring equal to, I'll use accuracy, and for number of jobs I'll say -1. Okay, perfect. And then I'll say grid underscore search and fit the data, x underscore train, y underscore train. And then finally, let's go ahead and display the best parameters and the score also. So I'm going to say print f of best parameters is grid underscore search dot best parameters. Perfect. I will also say print f of best cross validation accuracy is grid underscore search dot best score. Let's display these out. Let's go ahead, clear it out, run it. So it looks like it's saying that I need to provide log to a square root. I'm not sure what I'm doing wrong here. Maybe I need to provide it in curly brackets or something. But again, it worked. And what we have here is we can see the accuracy base 96, and then here 9626. Let's see if it's increased. It's actually reduced based on the parameters that are provided. Max depth none, max features it used square root, and n estimators it used 200, and the accuracy that it got is 0.962. So this is how you can train a random forest classifier on a dataset, tune its parameters, and evaluate its performance. The performance is not as good as compared to what we had. Maybe my values were not good and probably have to work more on getting a better grid here and give a better parameters to have a better performance. But again, this is the entire process of building a random forest classifier and tune its parameters and evaluating its performance. I hope you were able to follow along. If you have any questions, do let me know. And then just to go over the summary, we went and understood the concept of bagging and how it reduces variance in machine learning models. We learned the architecture of random forest and how they improve performance compared to the single decision trees. We gained hands-on experience tuning hyperparameters to optimize the random forest model, and we observed how random forests handle classification task effectively through feature randomness and bootstrap sampling. I hope it was helpful. If you have any questions or had any issues, let me know and I'll get back to you. Day 3, Boosting and Gradient Boosting. Today we're going to look at the concept of boosting first. What is boosting? Boosting is an ensemble technique that sequentially combines weak learners, which are models with performance slightly better than the random guessing, to form a strong learner. Now, each subsequent model focuses on correcting the errors made by the previous models. Now, how does boosting differ from bagging? Here is a table displaying that. So, the feature for bagging is approaches trains models independently on bootstrap subset, whereas boosting trains model sequentially to correct the errors. The purpose of bagging is to reduce variances by averaging predictions, whereas boosting reduces bias by focusing on difficult cases. Examples of bagging, we already saw one, random forest, yesterday, and for boosting, we're going to look at gradient boosting, and then there's adder boost. Now let's look at gradient boosting in more detail. What is gradient boosting? Gradient boosting is a boosting algorithm that builds models sequentially by minimizing a loss function using gradient descent. It iteratively adds weak learners, usually decision trees, to improve overall model performance. Now, how does gradient boosting work? First, you initialize the model. You start with a simple model, often predicting the mean of the target variable. Then you compute the residuals. Calculate the difference, the residual between the actual and predicted values. Next, fit the weak learner. Train a weak model. Example can be a shallow decision tree to predict the residuals. Next, you update the prediction. You add the predictions of the weak learner to the overall model. Then repeat. Continue adding weak learners until the desired number of iterations or a stopping criteria is reached. Let's talk about the key parameters in gradient boosting. We have the learning rate, which determines the contribution of each weak learner. Its smaller values reduces overfitting but requires more iterations. Now we have number of estimators is the number of weak learners trees added sequentially. Larger values improve learning but increase also the computation time. And then we have regularization. Techniques like limiting the depth or adding penalties to prevent overfitting. Next, let's talk about understanding the key parameters. We have the learning rate or learning underscore rate. Lower, lower values improve model performance by reducing the overfitting but require more iterations of learning rate. Typical range that we use is 0.01 to 0.3. Number of estimators or n underscore estimators represents the number of trees added to the ensemble. Larger values can improve performance but it's risk overfitting. Next, we have tree depth or max underscore depth. It limits the complexity of individual tree, and in this case, shallower trees generalize better but might underfit. With all this information, let's jump into our hands-on exercise for today, where we will be training and evaluating a gradient boosting model on a dataset, tune key parameters, and compare its performance with random forest model. The dataset we'll be using is the same as last one, the breast cancer dataset, a binary classification task to predict whether a tumor is malignant or benign. So let's start with our step one, where we'll be loading and pre-processing the dataset. We'll go ahead, create a new file, save it as day 3 underscore exercise. Here I'm going to say from sklearn dot datasets. I need the dataset, so I'm going to say import load breast cancer dataset. From sklearn dot model selection, I will import the train test split. Now let's go ahead and first load the data set. So I'm going to say data equal to load breast cancer. Next I'm going to say x comma y equal to data dot data and data dot target. That will get me my target. Now let's go ahead and split the data set. To do that, I'm going to use train test split, pass it the values of x, y, test size equal to 0.2 and random state equal to 42. That will give me x underscore train, x underscore test, y underscore train, and y underscore test. So I have my data set. Now let's go ahead and first display some data set information. So I can print the features which we already saw in the last video or yesterday. Data dot features underscore names, that will give me the names, different features that we have, and then I want to also see the target names, that will give me the classes, let's say in this particular case, and then let's go ahead and run it and check it out. Python day 3. There you go, we have our features and the classes available. Perfect. Our next step is to train a gradient boosting model. This time we train a gradient boosting model using scikit-learn's gradient boosting classifier and evaluate its performance. So for that, so I'm going to go ahead and from sklearn dot ensemble import the gradient boosting classifier. Next, sklearn dot metrics, we will, for evaluating, we are going to use accuracy score, and we'll also display the classification report just to compare with yesterday's data. So once I have that, next thing that I'll do is I'll train the gradient boosting model. To do that, I'm going to say gb underscore model equal to gradient boosting classifier, give it a random state of 42, gb underscore model dot fit, I'm going to fit x underscore train and y underscore train. Perfect. Now it's time to predict. So I'm going to say y underscore pred underscore gb equal to gb model dot predict and give it x underscore test data set. So once I'm done with that, now I can go ahead and evaluate performance of this model. I can say accuracy underscore gb equal to accuracy score and pass it y underscore test and y underscore pred gb. Let's go ahead and print these data out so we can check it out. I'm going to say gradient boosting accuracy is accuracy gb 0.2 f. I want to see the entire thing, so just 2 decimal places is good, /n classification report /n comma classification report, and to this I'll pass the same parameters. Perfect. So that should do it. So let's go ahead and test this out before we tune the parameters. So I'm going to go here, clear, run it again, and we have our gradient boosting accuracy of 0.96, and this is the classification report that we have. Perfect. So let's go back and let's do the tune parameters step, where we'll experiment with different learning rates and number of estimators to optimize the model performance. So first I am going to say, let's define a hyperparameter grid. Also, I need that from my model selection, I would need the grid search CV. So I'm going to just do it there. So I'm going to say parameter grid equal to, I will be using first the learning underscore rate, as I said. So I'm going to say try to use 0.01, 0.1. As I mentioned, we give from anywhere from 0.01 to 0.3 depending on what you prefer, and let it play with it right now. N underscore estimators is, I will give the values between 50, 100 and 200. So let it decide. and then I'll give a max underscore depth. I'll give either use 3 trees, 5 or 7. So tell me which one is better. Now let's do a perform the grid search. To do that, first let's create the grid search variable, which will use my grid search CV, and it needs the parameter. First it needs the estimator, which is our gradient boosting classifier with a random state of 42. Next I have the param grid, which is param grid that we created. Next we need CV equal to 5. Next we need scoring equal to, I am going to use accuracy, and n underscore jobs equal to -1. And then finally I'll say grid search dot fit. I'll fit it with the data x underscore train and y underscore train. Perfect. So that's fit. Now next is, let's go ahead and display our best parameters and score. So to do that, I'll say print f of best parameters is grid underscore search dot best parameters. Next I'll say print f of best cross validation accuracy. What is the best one that it can provide us? Grid underscore search dot best underscore score equal to 0.2 f. So that's what it is. So next step is to compare the gradient boosting with random forest. But for now, I'm going to save this and run it and see how it looks like. So we have our this best accuracy just by gradient boosting. Now let's, after the tuning of the hyperparameters, let's see what we get. It's going to take some time. And there you go. Learning rate is 0.1, max depth is 3, and n of estimators equal to 200 based on the data we provided. And the best cross validation accuracy it can give us based on these parameters is 0.96. Our next step, as I mentioned, is to compare the gradient boosting with random forest. So I am going to go ahead and from my ensemble, I'm going to also get random forest classifier. Next, I am going to train the random forest here. Say rf underscore model equal to random forest classifier, random state equal to 42. Next I'm going to say rf underscore model dot fit. I'll pass it x underscore train and y underscore train. Next, to predict, I will say y underscore pred of rf equal to rf dot model, rf underscore model, sorry, dot predict, and pass it x underscore test. Next, based on that, let's get the accuracy. So I will say, based on the data that we have, let's evaluate the performance. To do that, I'll say accuracy underscore rf equal to accuracy score y test versus what we got under y pred rf. Now let's go ahead and print our random forest accuracy, that is, oops, I can do it inside, accuracy rf 0.2 f. Now we already have the gradient forest boosting accuracies before, so we can just compare them. Clear, run it again. So our gradient boosting accuracy is 0.96. Now after we do hyperparameters, we also found that the accuracy for that is 0.96. Now after doing, if I can type properly, that is, let's go one more time. It's going to take a little bit time. So again, gradient boosting accuracy is 0.96. After doing the tuning the parameters, we get 0.96, and with random forest accuracy, we're also getting 0.96. If I remove these, let's see to the decimal point how good they are. I'm going to just to have fun with it. So 0.95614 is the value here, 0.56. So, and that is without tuning the hyperparameter. Once we tune in the hyperparameter is 0.964, which is better than as compared to random forest 0.9649 versus 48. So random forest is still better as compared to the others that we have used here. So, just to summarize, today we understood the concept of boosting and how gradient boosting builds sequential models. We learned the importance of tuning hyperparameters like learning rate and number of estimators, and then we gained hands on experience training and optimizing a gradient boosting model. And finally, we compared the strengths and weaknesses of gradient boosting versus random forest. I hope you were able to follow along and get through this project. If you had any issues or errors that you saw, let me know and I can help you out with them. Day 4, Introduction to XGBoost. Let's go over first XGBoost of what is XGBoost. XGBoost, or also called as extreme gradient boosting, is an advanced implementation of the gradient boosting algorithm designed for speed and performance. It introduces various enhancements that make it faster, more efficient, and capable of handling complex datasets. Let's talk about improvements over traditional gradient boosting of how it helps. First, speed. Implements parallel processing to speed up computations. Handling missing data. Automatically handles missing values by learning optimal split directions. Regularization adds L1 lasso and L2 ridge regularization to reduce the overfitting. Custom loss functions allows users to define custom loss functions for specific needs. And tree pruning uses a max depth parameter to prune unnecessary branches, improving computational efficiency. Let's look at some of the key features of XGBoost. Handling missing data automatically assigns missing values to the branch that minimizes the loss function. It reduces the pre-processing steps for data sets with missing values. And regularization includes penalties for overly complex models, reducing the overfitting. Hyperparameters that are used are lambda, which is L2 regularization term, and alpha, which is the L1 regularization term, and parallel processing. It splits the calculations for tree construction across multiple cores, significantly improving your training time. Let's talk about the hyperparameters in XGBoost and how to tune them. So first, the key hyperparameters are learning rate, which is ETA, controls the contribution of each tree to the model. Typical range is 0.01 to 0.3. Next, we have a number of trees, which is N estimators, determines the number of boosting rounds. Larger values may improve performance but increase the computation time. Next, we have tree depth, which is max underscore depth. Limits the depth of trees, balancing bias and variance. Shallower trees generalize better, while deeper trees may overfit. Your subsample, a fraction of data used to train each tree, helps reduce overfitting. Typically, range is between 0.5 to 1.0. Then we have call sample by tree, fraction of features used for each tree split. Typical range is 0.5 to 1.0. And finally, we have the regularization parameters, lambda and alpha, which control L2 and L1 regularization respectively. Now let's go ahead with an hands-on exercise for this, where we'll be training an XGBoost model on a data set, tune hyperparameters using cross-validation, and compare its performance with a gradient boost model. We'll be using the same data set, the breast cancer data set that we used earlier yesterday, which is a binary classification problem. So let's go ahead. First, this time, instead of starting a project, we'll start a project. Why not? Save it in day 4 underscore ex.py. But we'll go to terminal, make sure we're in the right folder, And here we will say pip install xgboost. It doesn't come by default, so you have to go ahead and install it. I've installed it earlier, so that's why it was pretty quick, but for you it might take some time if you're doing it first time. Now next, let's go ahead and get the Python imports. So I'm going to say import xgboost as xgb. Next, I'm going to say from sklearn dot datasets. I need that dataset on import load breast cancer. Next, I'm going to say sklearn dot model selection. I am going to import train test plate, and for the grid of parameters or the grid search, I'm going to use grid search CV. Next, I'm going to say for matrix, I will import accuracy score and classification report. Perfect. So I have that. Next step is to load and pre-process the data set. So I am going to say load the data set, which is data equal to load breast cancer, and then x comma y equal to data dot data and data dot target for y respectively. Next, I'm going to go ahead and split the data set, and I'll get x train x x underscore test y underscore train y underscore test equal to train test split x comma y comma test size equal to 0.2 and random state equal to 42. Next, I will go ahead and display dataset info. So for that, I'll say print f of features, which are data dot feature underscore names, and then I'll display the classes, which are f classes data dot target underscore names. Perfect. We've done this before, so I don't want to run it again. So I'm going to go to the next step, which is train an XGBoost model. So first, I'm going to go here and say convert data set to D matrix. Now this is the optimized data structure for XGBoost. The way we do it is we say dtrain equal to xgb dot D matrix. And this is first time I'm using these, so that's why they are not going to autocomplete. Xtrain and label equal to y underscore train. Next, I need dtest, which is xgb dot D matrix, and inside the function is x underscore test and label equal to y underscore test. Perfect. So that kind of creates my D matrix. Next, I will go ahead and train XGBoost model. Now to do that, I'll say first I need the parameters. Parameters are, I'm gonna move it up so it's clear. First is objective, and objective I specify, I say I want to do a binary logistic regression here. Next, I say the eval metric is in this case log loss. That's what I'm going to specify, log loss. So you can actually specify whichever you like for the evaluation metric. Next, I'm going to say max underscore depth that I want to use in this case is 3, and I can say ETA is 0.1. If you remember, ETA is the learning rate that we use, and that's what I mentioned here. Next, let's go ahead and take the xgb underscore model equal to xgb dot train. I'll pass the params to it. I pass the dtrain to it. I'll pass the number of underscore boost underscore rounds of how many rounds do I want of this XGBoost equal to 100. More like iterations is 100 I want. Next, I'll say go ahead and predict, and I'm going to say y underscore pred equal to xgb underscore model dot predict, pass it dtest, which we created earlier, the dtest dataset, greater than 0.5 as type int. So since it's a classification, I need 0 and 1, so that's why I'm mentioning that. Next, let's go ahead and finally evaluate the performance. To do that, I am going to say accuracy equal to accuracy score and pass it y underscore test and y underscore pred. So compare those. It looks like I pressed the cap or shift a little early. Y pred, and then now print. In this case, I am going to say xg boost accuracy is accuracy. Let's not use the point here because it doesn't give me the best results. Let's say slash n classification report with this is slash n comma classification report y underscore test and y underscore pred. Perfect. I think everything is good for now. Let's see. XG push is giving me warning, but already added the library. Let's hope it works. So let's clear it out, and I'm gonna say python day4 dot underscore ex. I have an error here which says xgb train. Something is wrong here. Let me look at it. xgb, where did I create it? Here. Oh yeah, I think I said number of boost rounds, not rounds, round equal to 100. That was the error. I think it does specify here. So I'm going to go ahead and run it again. And there you go. We have accuracy of 0.956. And this is a classification report based on the XGB boost. Pretty good. Almost all in above 90s. So that's a good table we have of the classification report. Our next step is to do hyperparameter tuning with cross validation. So for that, I'm going to go back here. I need the from XGBoost. I need one more thing. I will import something called as, did I spell XGBoost right? Yes, XGBoost XGB classifier. That's what I need. So first, I'm going to go here and say define the hyperparameter grid. Same thing that we did earlier. Say param underscore grid, and here I will give the grid values, which are, first one is the learning rate. That I want to specify to 0.01, 0.1, and 0.2. Next, I want to give the n underscore estimators, which I will give from 50, 100, 200. Next, I want to give the max depth, which will be either 3, 5, or 7. Pick which is the best. Next, I can give the subsample. So that I will specify between 0.8 and 1.0 to pick the best one. Next one, I'm going to go for column sample by tree. This I will specify to be again 0.8 and 1.0. Here's this, which columns to use, and then I'm going to say initialize XGBoost classifier. So do that. I say XGB underscore classifier or CLF equal to XGB classifier. It needs some parameters like user underscore label underscore encoder. I'll set that to false. Next we have eval underscore metric equal to I'll say log loss, and then I'll have to give a random state for this, random state. Since it's first time I'm doing it, everything I have to hand type. Doesn't help me. I think user label encoder has been removed in the latest version, but we'll check it out when we run it. Next thing that I want to do is I want to perform the grid search based on the parameters that we've given. So I'm going to say grid underscore search equal to grid search CV. Give the estimator as xgb underscore classifier. Next, I need the parameter grid, which is parameter grid. Next, I need the cross validation of 5. Next, I am going to say the scoring type that I want to use is accuracy. Next, n jobs, I'll say n underscore jobs equal to -1. I'll keep that consistent as others that we've done till now. And then finally, I'll say grid underscore search, and to this I'll fit my x underscore train and y underscore train. Save that. Now let's go ahead and display the best parameters and score. So I say print first one is best parameters grid underscore search dot best parameters is what I'll specify here. Next, let's go ahead and print f of this one is best cross validation accuracy, which I'll mention grid underscore search dot best score, and I'll leave it as it is. Perfect. Now next is to compare the XGBoost with gradient boosting, but for now let's run this and check if some of my predictions are right or wrong. So here you go, user label encoder has been removed, so I can just remove that, clear it out. Let's run it again. So there you go, we have by XGBoost the accuracy is 0.95. The best cross validation based on the parameters that we've given is 0.97, much better than the actual accuracy, so that's good. And it picked up the best parameters as 0.8 for call sample, for learning rate 0.2, max depth is picked 5, and n estimator is 200, subsample is 0.8. Perfect. So I have that. Now the next step, as I mentioned, is to compare XGBoost with the gradient boosting. For that, first let's go ahead. Do I have ensemble? No. So I am going to say sk learn dot ensemble. I am going to import the gradient boosting classifier. Go at the bottom and train the gradient boosting model. To do that, I'll say GB model equal to gradient boosting classifier, give a random state of 42. Next, I'll say GB underscore model dot fit with X underscore train and Y underscore train. So we have model train. Now let's go ahead and get the predictions. Underscore GB equal to GB model dot predict and give it the data set X of test. Now let's go ahead and evaluate the gradient boosting performance. To do that, I can say accuracy of GB equal to accuracy score and pass it y underscore test and y underscore pred of GB, and then I can now print the gradient boosting accuracy, pass it accuracy GB. Perfect. And then we can compare the results with the others. So let's go ahead. It's already clear. So I'm going to run the project. So our accuracy with XG boosting is 0.95614, with the best with after parameter tuning is 0.97. But if you look at gradient boosting as compared to XG boost, 0.561403508777193, exactly same as XGBoost, even though it is supposed to be better than gradient boosting, but based on the data set, I think it's gives you exactly same number to the point. So perfect. So that kind of showed you how we can use XGBoost, how we can tune XGBoost model, and finally we compared with the gradient boosting. So just to summarize, we went and understood the key advantages of XGBoost over traditional gradient boosting. We learned how to train and evaluate a XGBoost model for binary classification. Also, we gained some experience tuning XGBoost hyperparameter using the grid search. And finally, we compared XGBoost with gradient boosting to understand the relative strength and weaknesses. Here, it turned out to be exactly pretty much same, but with hyperparameter tuning, XGBoost kind of blew it out the park and it did a pretty good job. If you have any problems or had any issues or have any questions, let me know in the messages and I'll get back to you. Day 5, Light GBM and Cat Boost. Let's start with Light GBM. Introduction to Light GBM. What is Light GBM? So Light GBM or Light Gradient Boost Machine is an efficient implementation of gradient boosting designed to handle large datasets and high dimensional data with speed and accuracy. Some of the key features of Light GBM are its histogram based splitting, which means it uses histograms to discretize continuous features, reducing memory usage and computation. Leaf wise tree growth grows the tree by adding splits to the leaf with the highest loss, improving efficiency but potentially overfitting if not regularized. Support for GPU training. Accelerate training using GPU computation. Handling sparse data. Efficiently handles dataset with missing or sparse values. Let's look at some advantages of Light GBM. First, it's faster training than XGBoost, handles large datasets effectively, and reduces memory usage with histogram based splitting. Now, when to use Light GBM? When you have large datasets with numerical features, that's one. And next is the time sensitive task requiring fast training. Let's talk about overview of Cat Boost. Now, what is Cat Boost? Cat Boost is a gradient boosting library developed specifically to handle categorical features without the need for pre-processing like one hot encoding. The key features of Cat Boost include its native support for categorical data, uses statistical encoding for categorical features, preserving order and relationships. Ordered boosting reduces prediction bias by using a permutation based scheme to train models. Robust to overfitting implements built in regularization methods, and that's why no overfitting most of the times. Advantages are it eliminates the need for manual encoding of categorical data, reduces overfitting with robust boosting techniques, and easy to implement for datasets with many categorical features. When to use Cat Boost? When you have datasets with a high proportion of categorical features, when your applications where overfitting is a concern, that's when we use Cat Boost. Now let's look at a comparison of XGBoost, Light GBM, and Cat Boost. Here is a table where it shows we saw the feature with speed, then XGBoost is moderate, Light GBM is fast, and Cat Boost is fast. When you have to handle categorical data, XGBoost requires encoding. Light GBM also requires encoding, whereas Cat Boost has native support. When you have memory usage, XGBoost is moderate and Cat Boost is moderate, Light GBM is low. For tuning complexity, XGBoost is moderate, Light GBM is high because it has leaf-wise growth, and Cat Boost is low. And best use cases for XGBoost is general purpose models, Light GBM is large datasets, and Cat Boost is categorically heavy datasets. Next, let's jump into our hands-on exercise where we will train and compare Light GBM, Cat Boost, and XGBoost models on a dataset, focusing on their ability to handle large datasets and categorical data. We will be using the Titanic dataset for this example. So let's get started. First, I'm going to create a new file. save it in my day 5 underscore exercise.py. Here, let's start with importing pandas as PD. Next, we need from sklearn dot model selection import train test split. Next, from sklearn dot preprocessing import label encoder. Now let's load the Titanic dataset, and do that by giving this URL. Just to check it out, I am going to open this in Chrome. Here it is. It has passenger ID, survived, P class, name, sex, age, SIB-SP, parch, ticket, fire, cabin, and embark. These are different fields that we have. So I am going to go ahead and make sure we read the CSV file from this URL. Next, let's go ahead and select our features and target. Since we don't care about everything, features I will pick, or X, you can give whatever name you want. I want to use, let's copy this, paste it here. I need P class. I want to use, comma, remove this, sex. I'll use age. I'll use fair, and did I remove, and I'll use embarked. So these are the ones that I need for my features. Okay, let's close this. Next, for my target, I will use the survived column. Okay, perfect. So I have that. Let's handle the missing values. Handle missing values. To do that, I usually have, I know that there's missing values in age. So for age, I am going to, I'm going to use the new fill NA method, where I will fill age with the value of df of age dot median. That's the function. And then I will say in place equal to true. Same thing I'll do for embarked, because that also has some empty values. I will say embarked, and instead of median, I'll use mode 0. So perfect. So I have that. Next, let's go ahead and encode our categorical variables. So for that, I'm going to say label encoders. Initially, I will set it as empty. Next, I'm going to say for column in, because I know in sex we have male and female, and in embarked we have another categorical variable, where, so if you see the data set here, embarked has this SC. So for those, I am going to say LE equal to label encoder, initialize that. Next, I'm going to say df, depending on which column it is, I will say LE dot fit underscore transform that particular column. Next, I'll say label underscore encoders for the column, use LE. Perfect. So I have that. Next, I am gonna split the data. So for that, I will say x equal to df of features and y equal to df of target, because we've just created df and the features here and target, but we are putting in the data frame right now, putting in the variables target and features. Now let's go ahead and call the train test split method, where I'll pass the features, the target, and my test size equal to 0.2 and my random state equal to 42. This will give us x underscore train, x underscore test, y underscore train, and y underscore test. Perfect. So I have that. Now next, let's go ahead and print some information like, oops. First, I'll say training data shape. Let's print that out, how it looks like. X underscore train dot shape. Same thing I'm going to do for test data shape. X test data shape is x test dot shape. Perfect. So this will complete a step one, which is load and pre-processing the data. So let's go ahead and see if everything is fine. I'm going to say Python day 5, run it, and I have my shape with 712 rows and 5 columns, 179 rows and 5 columns. Perfect. So I have that data. Next step is to train a light GBM model. So for doing that, I am going to go up here and import light GBM as LGB. Next, from sklearn dot metrics, import accuracy score. So these are the two things that I need. Now let's go at the bottom and first train the light GBM model, that is LGB underscore model equal to LGB dot LGB MC. I think that's the classifier, M classifier. So LGBM classifier is the class that I'm going to use. So I'm going to initialize that LGB underscore model dot fit. Inside this, I'm going to say X underscore train and Y underscore train. So my model is trained. Now next, go ahead and predict and evaluate. So predict LGB underscore pred equal to LGB underscore model dot predict. I am going to say X underscore test, and now go ahead and print F light GBM accuracy is accuracy score Y underscore test LGB underscore pred, and I'll say let's use 0.4f because 0.2f is not always perfect. Now go ahead and run this code, and here is my light accuracy so it has some warning like no further splits with the positive gain. So I don't care about that. Start training from this is where it started, and then it said no positive gain, so that's why it stopped, and it gave me a light GBM accuracy of 0.80. So that's my accuracy. So clear this out. Let's go ahead and now let's train a cat boost model. So for cat boost model, I am going to go ahead and say from cat boost import cat boost classifier. So we just get the classifier directly from here. Now let's go ahead, and next step is to train the cat boost model. To do that, I will first say cat underscore features equal to p class comma sex comma embarked. So what I'm doing is I'm specifying which ones are the categorical columns, because as I mentioned, it has a native implementation for categorical columns for encoding them and making sure you don't need to do it yourself. Say cat model equal to cat boost classifier cat underscore categorical features equal to categorical features that I've created above. Next, I'll say verbose equal to 0. So there you go. We have our model created here or initialized. Then I'll say cat model dot fit. So train it with the data x underscore train comma y underscore train. Then finally, we'll go ahead and predict and evaluate. Now it's exactly same as this here. Just the difference is instead of LGB, we'll see cat pred. We'll say cat model pass x test print cat boost accuracy is accuracy score y test, and instead of this, I'm going to use cat display it out. Let's compare both of them for now, light GBM and cat boost. So I'm going to go here, clear, it's already cleared. Let's run it. And there you go. We have our light GBM accuracy of 0.8 and we have cat boost accuracy of 0.81. So cat boost accuracy is better than light GBM. That's what I would say right now. Let's go ahead and compare it with XG boost. So I am going to go ahead and say from XG boost import XGB classifier. So that's our XGBoost classifier. I'm going to come down and do the exactly same thing that I did with the others too. I'll say train XGBoost model. So I'll say XGB underscore model equal to XGB classifier, and I'll say use underscore label underscore encoder equal to false. Actually, this is not useful anymore. I'll say eval underscore metric equal to log loss. The use label encoder was used for the previous version, so we don't need that anymore in the latest version. Unless you have the older model, then older version of XGBoost, then you have to specify use label encoder to be false. XGB underscore model dot fit, say x underscore train and y underscore train. Next I'll say predict and evaluate. This is exactly same as the previous one. I'll take that data, move it here, and I'll say XGB, copy that is XGB model, predict this data, and this one is XG boost, accuracy is accuracy speeds, this one, and remove the cat and put it here. Go ahead, clear it out, run it again, and we have light and all three of them 80, 81, and 77. Now if you compare, cat boost has the best one for this particular data set, light GBM is second best, and the worst that we have here out of the three is XG boost is the third one with 0.77 accuracy. Next step is, let's go clear this out, is to experiment with handling categorical data in cat boost. So we already did some encoding, but what I'm going to do here is I'm going to show you train cat boost without encoding categorical features. So we already encoded earlier for the other systems to use, but what if I don't? So what I'm going to do is I'm going to say cat underscore model underscore native equal to cat boost classifier cat underscore features equal to sex and embark. These are the ones that we encoded. So I'm going to say these are the ones that I want to use, comma verbose equal to 0. Next I'm going to say cat underscore model underscore native, and this one I will fit with the data. I'll say x underscore train and y underscore train, and then I'll predict and evaluate with this native model. I'll say cat underscore preds underscore native equal to cat underscore model native, and this one I'll ask to predict and I'll pass x underscore test. Now let's evaluate and see how did it do. I'll say cat boost native accuracy is accuracy score, pass it y underscore test and cat preds native, and if you want to do that 0.4f we can do that here. So that should take care of, oh, I think I forgot a closing bracket here. Perfect, so I have that. Let's look at the accuracy for this one. Run it again, cat boost, and now It's giving me an error saying accuracy score. Did I spell something wrong? Oh, close this. Accuracy score y test cat preds native colon. Something is not closed properly here. Okay, so I guess I had it. Clear it out, run it again. 81, 80, 77, and 8156. So if you look at it, the cat boost accuracy was already good, 8101. Now it's 8156. It's become much better without doing encoding. So you don't have to do anything when you're using cat boost. Just use the data as it is and it will work perfectly fine. So I hope you were able to follow along and get things done. Today, what we completed was we understood the strengths and limitations of Light GBM, Cat Boost, and XG Boost. Then we gained some practical experience training and evaluating models with these different frameworks. And then we learned how to handle categorical data effectively with Cat Boost. Finally, we developed the ability to compare and choose the best framework for a given data set. I hope you were able to follow along. If you have any problems, if you had any issues while implementing it, or if you have any questions, let me know in the messages and I'll get back to you. Day 6, handling imbalanced data. Now, before handling, let's look at some of the problems caused by imbalanced data in classification tasks. So, first, what is imbalanced data? Imbalanced data refers to data sets where one class significantly outnumbers the others. For example, in a data set with 90% negatives and 10% positives, a classifier predicting all negatives could achieve 90% accuracy while performing poorly for the minority class which is predicting positives. Now let's look at some of the challenges with imbalanced data. First is bias towards the majority class. Machine learning models tend to prioritize the majority class due to its frequency. Next is misleading evaluation metrics. Metrics like accuracy can be misleading as they do not account for the class imbalance. Limited information for minority class. Insufficient samples for the minority class can lead to underfitting. And what are the applications with imbalanced data? We have fraud detection, medical diagnostic, and anomaly detection. So think about it, if you have imbalanced data in any of these, it will cause a lot of problems. So now let's look at some techniques to handle this imbalanced data. First, let's look at the different resampling technique options. First is oversampling. You increase the number of minority class samples by duplicating or synthesizing new samples. Example here is SMOTE, synthetic minority oversampling technique, which generates synthetic examples. Next is undersampling. Reduce the number of majority class samples to balance the data set. Risk here is to loss of valuable information from the majority class. Next problem that we can solve is algorithm solutions. One is class weights. Assign higher weights to the minority class during the model training. Many algorithms like logistic regression, random forest have built in support for class weights. Next, anomaly detection models. You can treat the minority class as anomalies, focusing the model on detecting them. Next, let's talk about evaluation metrics for imbalanced data. So we have F1 score, which we can use for harmonic mean of precision recall, focusing on both false positives and false negatives. ROC-AUC measures the ability to distinguish between classes across various threshold values. And we have precision recall curve, which focuses on performance for the positive class. Now let's jump into a hands-on exercise. We will apply SMOTE to handle class imbalance, train a classifier, and evaluate its performance using metrics like ROC-AOC and F1 score. For the dataset, we'll use the credit card fraud detection dataset, which is highly imbalanced, containing transactions classified as fraudulent, which are minority class, or non-fraudulent, which is majority class. This dataset is available from Google APIs. So I'm going to go ahead and jump into creating a new file and call it day6 underscore exercise.py, and we'll start with importing pandas as PD. Next, I will use sklearn dot model selection and import train test split. So we're just going to do load and explore the data set for the first step. So let's go ahead and load the data set. The data set is available at this URL, https storage.google.api.com/download.tensorflow.org/data/creditcard.csv. So you can download from there or use it directly from there by saying pd dot read csv and pass the URL here. Next, let's go ahead and explore this data set. So I am going to say print. You can directly open it in a browser. That's one way of exploring it. Or you can just say dataset info, because you can get some basic information here in a tabular format. Print df dot info. And then next thing that I need is class distribution /n. To show that, I will say print df, the class that we have here, dot value counts. It's a function, so I'm going to call that. Next, let's also split the data set and keep it ready. X equal to, usually we do df dot, I am going to drop columns equal to class, because that's the one that I want to use as target, which is y equal to df of class. Perfect. Next, let's go ahead, x underscore train, x underscore test, y underscore train, and y underscore test equal to train test split, and pass it the x y test size equal to 0.2 and random state equal to 42. Perfect. So I have that. Let's go ahead and run this and look at the data set first before we start to train a classifier on the original data set. So Python day 6, and there you go. We have our data set. It might take some time because, as you can see, it has 284,000 rows. It's probably in MBs, this particular file. The memory usage is 67.4 MB, and these are all the different columns that are available here. And class is what I'm interested in, which is int64 at the end of it, which is our target. So we can see all the data set, all the data over here. Pretty much all of them have data. Looks like there's no empty data, so it's all clean. That's good. So now with that, let's go ahead and train a classifier on the original data set. So for this classifier, I'm going to use the random forest classifier. So I say sklearn dot ensemble. I am going to import random forest from there classifier, and then for metrics, I'm going to say sklearn dot metrics. I am going to import our classification report. I will get the ROC AUC score, because that's what we will be using, as I mentioned. So now next step is, let's go ahead and train the random forest. Now if you remember how we did this earlier, we said rf underscore model equal to random forest classifier. I will use a random state of 42. I will also use class weight equal to balanced. Okay, this will balance our the data set. Next, I'll say rf underscore model dot fit and x underscore train and y underscore train. Again, the reason I said balanced here is because we have a lot of no class versus class, like non-frauds versus fraud in the data set. So balanced makes sure that it's properly balances the data sets based on the input that we provide. Next, I am going to go ahead and predict and evaluate. To do that, I'll say y underscore pred equal to rf model dot predict, and I'll give it x underscore test to it. Next, I'll say print /n classification report. This is on the original data set that we have /n and print classification report. For classification report, I need two, which is ytest and ypred as parameters. So that's good. Next, I will say roc underscore auc equal to roc auc score. Pass it y underscore test rf underscore model dot predict. So this thing needs the predict proba. That's what I'll have to provide here. X underscore test, and inside that I'm gonna pick colon to 1. So that's what I'm gonna pick from there, and that's what I need as input. So let's print this f roc dash auc on the data set with the values. So I'm gonna say here roc underscore auc point to f. Perfect. So I have that. Next thing I'll have to do is apply the smooth to handle the imbalance. So I'm going to run that right now. If you want to see this, I can run it because it's going to take some time. So I'm going to leave it there. And at the same time, I will go here and apply smooth. So from imb learn dot oversampling. So this is a separate library and I've not used it before. So that's why it's not showing me, not pre-filling it here. So now to apply smooth, I'll say apply smooth here. To do that, I'm going to say smooth equal to SMOTE smooth random state equal to 42. I'll give that seed as same 42. Next, I'm going to say X underscore resampled Y underscore resampled equal to smooth dot fit underscore resample. I'll pass it X underscore train and Y underscore train. Let's see if the code ran, and it did run, but it's not complete yet. It's still doing the analysis over here. So I'll give it some more time and come back. Next, I'm going to go ahead and display the new class distribution after I have sampled the data. So for that, I'm going to say print /n classification or sorry, not classification, class distribution after smooth is /n print. I need pd dot series, pass it y resampled dot value counts. This will show me the difference based on what it was before this class distribution and now after the class distribution. So if you see here, we have our class distribution from before where it shows this data here. 0 is 28,000. As you see, it's very biased, it's not balanced. And here is our ROC AUC because it took some time, it ran, and finally we got the ROC AUC, which is 0.95 for this, which is pretty good. Now, after applying smooth, let's print this part. So I'm going to clear it out, run it again. I'm going to leave it and go back and do the what I'm going to do is I'm going to train a classifier on the resample data now. So I am going to use the same random forest. I'm going to say train random forest on resampled data. Do that. Where is my previous one? Here. We use this rf model underscore smooth. I'm going to say random forest classifier. I don't need to have to specify because it's resampled now. Rf morphed, underscore smart fit, and instead of this I'll give X resampled and Y resampled. That's it. Now let's go ahead and predict, and so same thing what we did here. I'm going to predict and evaluate based on this. In this particular case, RF model, let's say this also smooth. Ypred smart, RF model smart, predict X of test, print with the sprint report, classification report. Let's say with smart is classification report Y test and Ypred smart. That's what I see. ROC AUC. Let's calculate that also. Let's see what is the ROC AUC score. ROC AUC with smart is ROCAC score, Y test, RF model, and this time SMOT, predict, proba, X test, good, and then ROCAUC with SMOT is ROCAUC SMOT. Perfect. So that's my final thing. Now, if you want to compare the results, we can compare separately, but we already have it here. So I'm not going to print more statement to compare. We'll just go up and down a couple of times to see this data values. I am going to save this, go back here, and here you'll probably see this was after I applied, created the resample data. If you see the class now here, 200 and sorry, 227,451, and it was 284,315. So you can see clearly the difference. Now with the data, before it was 0.95, now with the smart, let's see what is the value. I'm going to run it and leave it for a little while until it completes. It took a little bit time, but finally we have our results here. So this is our initial class distribution where we have zeros bunch of times and ones, which are fraudulent charges at 492. But after the smart effect, we have 227,000 equal number of positives and negatives. So it added some synthetic data to it. And if you look at the ROC AUC is 0.95, and after smart the ROC AUC is 0.98, much better. And here is a classification report. If you look at that, it's a little bit different for different fields, but that's what you get after smart and before smart. So I hope you were able to follow along and get these where we were able to have a data set with lower recall and F1 score due to the class imbalance, and we applied smart and improved the recall and F1 score and addressed the imbalance, and we highlighted the importance of handling. If you see, handling the imbalanced data in improving the model's performance. So I hope you were able to follow along. But today we went and understood the challenges caused by this imbalanced data sets and their impact on machine learning models. We learned techniques like smart, oversampling, and undersampling to handle class imbalance. We gained proficiency in evaluating models for imbalanced dataset using F1 score and ROC AUC, and we observed how handling imbalance can significantly improve the performance of machine learning models. I hope you were able to follow along. If you had any questions or issues, let me know in the messages and I'll get back to you. Thanks. Welcome to day 7 and the last day of our week 7. And today we'll be looking at ensemble learning project, comparing models on a real data set. So we will be using the customer churn data set this time, and I've already downloaded it and put it in my folder. Here I have telco customer churn data set that is available, and you can download it from the website. Now, before that, let's go over some of the tools that we need to start. First, building and evaluating multiple ensemble models. Now, why compare ensemble models? Different ensemble techniques, example bagging, boosting, they excel in different scenarios. Comparing them helps identify the most effective model for a specific dataset or problem. Ensemble methods to consider are: first is bagging, which is random forest, reduces variance by averaging predictions from multiple independent models. Works well with high variance models like decision trees. Then we have boosting. Example is gradient boosting, XGBoost, and light GBM. It reduces bias by sequentially correcting errors from the previous models. Effective for complex patterns and imbalanced datasets. Comparing bagging and boosting. So for bagging, it builds models independently using random subsets of data. It's robust against overfitting with strong base learners. Whereas boosting, it sequentially builds models focusing on hard to predict samples, requires careful tuning to prevent overfitting. Next, let's talk about model performance on balanced versus imbalanced data. Now, challenge with imbalanced data that we saw earlier is models may prioritize the majority class, leading to poor performance on the minority class. Evaluation metrics, we use accuracy, which may not reflect true performance for imbalanced datasets. F1 score balances precision and recall, focusing on the minority class, whereas ROC-AUC evaluates the model's ability to distinguish between classes across different thresholds. Now, let's jump into our hands-on project, which is the ensemble learning and model comparison. Today's the objective is to train and compare multiple ensemble models on a real-world data set, analyzing their performance under balanced and imbalanced conditions. Dataset will be using the customer churn dataset, which predicts whether a customer will leave a service provider based on demographic and usage data. So I have the data already downloaded, which is our telco customer churn data, and it has that churn field at the end which says yes or no depending on when they will leave or not leave and their information. Now let's go ahead and first create a file, save it in our day 7 exercise. Next, first let's go ahead and import. So first we'll load and explore the dataset as we've been doing. Pandas as PD. Next, let's load the dataset, and my I don't have a URL here, so I'm going to say df.pd dot read csv, and the file name is, let's go ahead, get the file name, telco customer churn.csv. Now let's, from this dataset, we already saw the dataset, but let's display the dataset info and preview some of that. So I am going to say print dataset info /n and print df.info. Next, I will say print /n class distribution /n and print df. One that I'm interested is churn dot value count. So we'll count how many yeses and how many no's are there. Next, I'm going to say print /n sample data /n df dot head. So we see first 5 rows from the set. So let's go ahead and say Python day 7, and here we go. We have no 5174, which is 5 times more or 4 times more than yes, which is 1869. I think it's 3 times more. Anyways, so and the class distribution, these are different class info which talks about what are the different fields that are there. Churn is what I'm interested in, and if you look at the sample data, this is the sample data we have here. Perfect. So we have that. So next step is to pre-process the data set. So what I'm going to do is I'm going to handle missing values. Do we have any missing values? Looks like it's perfect. But still, if we had to handle the missing values and encode the categorical features, how do we do that? Next, we'll scale the numerical features for boosting the model. So I'm going to go here, and from sklearn, I will use the pre-processing inside there, and from there I will import a label encoder and standard scalar. So first, let's say if there were some values missing, handle missing values. So for example, if we had df of total charges, so that's a field over there, right? If I'm not wrong, total charges, which is also an object. So for that, I am saying pd dot to numeric. So I'm going to convert that. So total charges is an object, and that's why I want to make sure that it's not numeric anymore. Sorry, not object, and it's numeric. df of total charges, comma, errors equal to, I'll use course. Okay, perfect. Next one, I'm going to say df of total charges dot fill na df of total charges dot median in place equal to true. I'm so used to using the old method. I know if I run this, it will probably give me a warning saying that I'm using the wrong format. So I'm going to say df dot. So the way it shows you here too, that call the method, and then inside the method you say that the column total charges is, and then give it the value that you want to give, which is this value here, and then specify in place equal to true. So if you do that, you will not see this warning. There you go, no warning. Perfect. Next I want to do is encode categorical variables. For that I'll say label underscore encoder equal to label encoder, and for column in df dot select underscore d types, inside there I'm going to say include equal to, I need object because it's a type of object, dot columns. For these columns, what do I want to do? So for each column I'm going to say if column is not equal to churn, because I don't care about churn, then I'll say df column, whatever that column is, equal to label encoder, and label encoder dot fit transform df of column. There you go. So that will take care of the encoding. Next I will go ahead and encode the target variable, since we said we are not going to do that churn here. So I'm going to say target variable by saying df of churn equal to label encoder dot fit transform, and then df of churn is what I'll pass. So that's done. Now I'll say next scale the numerical features. So for scaling the numerical features, we'll use the standard scalar. So say scalar equal to standard scalar. Numerical features that I'm interested in are, let's see from the list here, I'm going to take tenure. I am going to take, do we have monthly charges? Yes, monthly charges, and we'll take total charges. So these are three that we'll take, and we'll say df of numerical features equal to scalar dot fit transform, and to it I'll say df of numerical features. Perfect. So that takes care of that. Now let's go ahead and split the data set. Split the data set by using x equal to df dot drop columns equal to churn. Let's see, df dot drop. Perfect. Next y, I mean when I say split, I mean features and target, y equal to df of churn. Perfect. So I have that. Now that has been done, let's go and handle the imbalance. I mean, this is optional, but it's good to do. So I'm going to go ahead and, so from imb learn dot over underscore sampling, I will import smart, and from sklearn dot model selection, I will import train test split, so we can split the data set actually. I'm going to go here and say split the data set x underscore train, x underscore test, y underscore train, y underscore test equal to train test split, and to this give x, I'll give y, I'll give test size 0.2, I'll give random state equal to 42. So there you go, we have that. Now let's go ahead and apply smart to it. To do that, we done this earlier this week. Say smart random underscore 42. Next I'll say x underscore train underscore resampled comma y underscore train underscore resampled equal to smart dot fit underscore resample. I pass it x underscore train comma y underscore train. So this is, as I say, smartified. Now, or resample, just to say in simple words, display class distribution after the smart. So now we have print /n class distribution after smart, so we can compare, because we did before earlier, we saw the class distribution was 5000 to 1800. So I am going to say smart /n print pd dot, we get the series where we pass y underscore train resampled and get the value counts of those. If I run this now, clear it out, and you see 4138, 4138 equal numbers. So now the data is not imbalanced. Next step is to train the multiple ensemble methods, models. So I am going to go here and get my models. So we'll get random forest from sklearn dot ensemble, import, I will get random forest classifier. I need XGB classifier, so that is from XG boost. I can import XGB classifier. Next, I want from LIGHT light GBM. I need import LIGHT GBM. I need LGBM classifier, if I'm not wrong. From sklearn dot metrics, I need to import, I need classification report, sklearn dot metrics classification report, and I need ROC AUC score. Perfect. Now let's go ahead and train using all these three different models. So first I'll say train random forest, then we will train XG boost, and then we will train light GBM. So let's get started. For this, I'm going to say RF underscore model equal to random forest classifier, random state equal to 42. Perfect. RF underscore model dot fit, and to this I'll pass x train resampled and y train resample. Perfect. Y underscore pred underscore RF equal to, now to predict, RF model dot predict and pass x underscore test. Next I'll say ROC AUC score for RF equal to ROC AUC score y underscore test, pass RF underscore model dot, if you remember this, predict proba, and I'll pass x underscore test of colon comma 1. So I have that, that's perfect. Now to do the same thing 3 times. So instead of doing 3 times, I'm going to copy this, paste, and paste. Now for the next one, which is XGB, XGB, instead of random classifier, it is XGB classifier. Now I'll read the random state here because I need that for this too, but it needs one more, which is metric equal to log loss, okay, comma. So that's good. And now I'll say XGB model fit. I'll pass the same resample data. Next, instead of this, I'll pass ypred XGB and XGB model predict xtest. ROC for XGB is ROC score, YRF model, not RF model, XGB proba x perfect. So this is exactly same. Next, same thing for this one. I'm going to use LGB, and here I am going to say LGBC classifier, and it needs the random state 42. Leave it as it is. Go ahead, remove this, remove this, remove this, remove this, and remove this. So let's just start again. LGB model fit train perfect. We have LGB model predict ROC LGB score is this, y test LGB predict proba x test perfect. So I have all those things. Now to display the data, I'm gonna say classification reports. Let's create the classification reports first. Say print. First one is random forest report /n, comma, classification report, pass it y test and y pred rf, because this is the random forest predictions. Next, for xg boost, we are going to say /n, again classification report y underscore test, comma, y underscore pred, and this is XGB, so XGB. Next one is for light GBM report /n, comma, classification report, to it passed y underscore test, y underscore pred, LGB. Perfect. So all of three of them. Now let's display ROC AUC comparison. So for that, I'll say print. Let's create a header. I'm going to say ROC AUC scores /n. Next, I'll say print f of, forgot the bracket. First one is random forest ROC underscore AUC RF point to F. Let's make sure everything is properly closed. Second one and third one. So next one was XG boost. For that, it was XGB. Next one was light GBM. That was LGB. Perfect. So I have everything up and ready. Let's run this project and see all the comparison. And there you go. We have the ROC AUC scores. For random forest, 0.83, XG boost is 84, and light GBM is 0.84. And above here, we have the classification reports for first one is for our random forest, XG boost, and light GBM. And before that, as we saw the churn data here. Perfect. So everything worked out pretty fine, and I hope you were able to follow along. And if you look at the ROCAC scores, it's pretty good. So we went through first with random forest. We observe its ability to generalize with the bagging. Then XGBoost, we highlight its performance on imbalanced data sets, and Light GBM emphasizes its speed and efficiency on larger data sets. That's what we have learned from here. Now let's go ahead and summarize what we learned today. Today we learned how to pre-process and handle imbalanced data from machine learning tasks. We gained hands-on experience training and tuning multiple ensemble models. We compare bagging and boosting methods to understand their strengths and weaknesses. And finally, we evaluated model performance using appropriate metrics for imbalanced data sets. I hope you were able to follow along. And if you have any issues or have any questions, do let me know in my messages and I'll get back to you.